So in this problem, a city bus starts from rest and accelerates at a rate of 1.5 meters per second squared for 10 seconds. It travels at a constant speed for 45 seconds and then slows to a stop at a rate of 2 meters per second squared. Find the maximum velocity and the total displacement of the city bus. Our first step in solving a problem is drawing a picture of the situation and establishing an origin and a positive direction. So I'm going to draw my bus, and I'm going to select the positive direction. I'm going to say that the bus is moving in that direction. Then I'm going to set out my knowns. So I know that I have 3 different sections of motion. The bus speeds up, then it goes at a constant rate, and then it slows down. So I'm going to write out my knowns for those 3 sections of motion, and I'm going to visually separate my paper for that. So when we're speeding up, we know that the acceleration is equal to 1.5 meters per second squared. We know it starts from rest, so we know that the initial velocity is equal to 0 meters per second. And we know that this happens for a duration of 10 seconds. When it's going at a constant speed, we also know some things. We know that the time it goes at a constant speed is 45 seconds, and that's all we know right now. And then we're going to slow down. And we know that the final velocity is equal to 0 because it slows to a stop. And we know that the acceleration is equal to negative 2 meters per second squared. We know that's negative because it's slowing down, and the vehicle is traveling in the positive direction. So in order for it to slow down, our acceleration is going to have to be in the opposite direction, so it will have to be negative. So that's what we know so far. Now we just start working through this. We know we need to find the velocity, the maximum velocity the car reaches. So let's use this equation on the speeding up, or let's use our speeding up knowns to solve for that. We know V final is equal to V initial plus AT. That's one of the equations that we derived from our graphs. So we can just plug in numbers and solve. So V final is equal to V initial, which is 0, plus acceleration, which is 1.5 meters per second squared. It's getting a little crammed, times time, which is 10 seconds. So we know that our final velocity is equal to 15 meters per second. And we can always double check our units here. We have meters per second squared times seconds. So that seconds on the top cancels with that second on the bottom, and our units are meters per second. Now we know that this final velocity is our constant velocity for the constant velocity part. So we can add that to our knowns. And then we need to know how far the total displacement of the city bus. So we need to know how far the city bus travels in each of these 3 segments. Let me change the view a little bit. Okay. So let's figure out how far the bus traveled in this time. We can use several different equations. I am going to use delta x is equal to V initial t plus 1/2 AT squared. And we know that V initial is 0, so this term goes away. So we plug in numbers. Delta x equals 1/2 times 1.5 meters per second squared times our time, which is 10 seconds. And we square that. So then we can double check with our units. We have meters per second squared, and then seconds squared there, so that cancels with that, and we're left with meters. So those are the correct units. And then we have 100 times 1.5, which would be 150, divided by 2, which gives us 75 meters. So the bus travels 75 meters for that portion. Now let's move to the constant velocity part. Now in this part, it's pretty easy. We can just use delta x is equal to vt, and that's one of our constant velocity equations. So we just multiply our velocity times our time. So we have 15 meters per second times 45 seconds. And we can double check our units there. We have meters per second times seconds, so that the seconds cancel out, and we are left with meters. And then we just calculate pretty easily there, 15 times 45, and we get 600, sorry, my calculator's not working. 675, which I should have done it in my head, meters. And like I said, this cancels out. All right. Now we can move on to the slowing down section. For the slowing down section, we know the final velocity is 0. We know that the object traveled at that constant speed of 15 meters per second until it started slowing down. So that v initial is 15 meters per second. And then our v final is 0 because it comes to a stop. So we need to find our total displacement, and we also need to find the total time. Maximum velocity and total displacement, so we don't need total time. So for this one, I'm going to use the equation v final squared equals v initial squared plus 2a delta x. And we know that our first step is to manipulate our equation to isolate our unknown variable. We are solving for delta x, so we're going to isolate delta x. So delta x is equal to v final squared minus v initial squared all over 2 times the acceleration. So we can plug in numbers. Delta x is equal to final, which is 0, minus initial, which is 15 meters per second squared, and then we divide by 2 times the acceleration. And we have to be careful. Our acceleration is -2 meters per second squared. We have to be careful of that negative. And we should see that we have a negative on the top and a negative on the bottom, so our answer is a positive value, which is what we expect. And we calculate that, we get 56.25 meters. Just to double check our units here, we have meters per second squared. That whole thing is squared. So you get meters squared over seconds squared. And then on the bottom, you have meters over seconds squared. So your seconds squared cancel, and then one of your meters cancels. So you're left with just meters on the top. All right, and then our last step is just to add them all together. So we have our total delta x is equal to 75 meters plus 675 meters plus 56.25 meters. And so we can quickly add that up, and we get our total displacement of the bus, which is 806.25 meters. All right, now there is the equation way to solve that problem. We can also solve this problem by using graphs, and I'm going to show you that way as well. I'm just going to quickly copy this, and then we'll add a new page, and we'll paste it. All right, so let's draw a velocity versus time graph for this situation. So we have velocity in meters per second, and we have time in seconds. We know that the bus starts from rest. It accelerates for 10 seconds. It accelerates at a rate of 1.5 meters per second squared. So we know that the slope is equal to 1.5 meters per second squared. Then it goes at a constant rate for 45 seconds. So this is going to be 55 seconds on my time axis. And then it slows down to a stop. And we don't know what that time value is, but we do know that the slope of this is equal to -2 meters per second squared. So now we need to find the maximum velocity and the total displacement of the city bus. We have so we know that the slope is 1.5 meters per second. We are looking for this value right here, which is our V final. So we know slope is equal to rise over run. So our slope is 1.5 meters per second squared. Our rise is what we're looking for. We're looking for that V final, and our run is 10 seconds. So we can just solve for V final there, and we see V final is equal to 1.5 meters per second squared times 10 seconds. So that gives us 15 meters per second. And that's the same thing we got before. So we know that this is 15. And then we need to figure out what this time value is so that we can figure out the area under the curve and figure out the total displacement. So let's go back over here. And we know, once again, slope is rise over run. So our slope is -2 meters per second. And that is equal to the change in x over the change in time. And we know that our change in x is our change in y over our change in x, which is change in velocity over change in time. Our change in velocity is -15 meters per second. And then, because we're starting at 15 and we're going to 0, and then our time is what we're looking for. So that's t. So we can solve that for t, and we get t is equal to 7.5 seconds. So that means that this value right here is going to be 62.5 seconds. And then our last step is to find the area under the curve. We know that the area under the curve is equal to displacement. So we can do a trapezoid equation for that. So delta x is equal to 1/2 times base 1 plus base 2. So our base 1 is 62.5 seconds, and our base 2 is 45 seconds. And then you multiply that by the height, which is 15 meters per second, and our result is delta x is equal to, I forgot what the value was, 806.25 meters. And we can see that our units work out there because we have seconds times meters over seconds, so that leaves us with meters. So that tells you how to solve this problem in 2 different ways, both valid ways, and you can try some on your own now.